time, wasn't it? So, welcome back. I hope you enjoyed your break. I know it's tough, but luckily this material is so good that sitting here, it's not going to be 2 hours, it's going to be an hour and 40 or something, isn't it? Sitting here for an hour and 40 is just a pleasure anyway. Okay, so we've been doing a lot of looking at Gaussian models, and what I've just been talking about, I mean, the reason we put the work in on that kind of boring, uninteresting linear Gaussian model is look at how it provided the foundation for what I think is a really interesting nonlinear model that does some very exciting things, and indeed all my research is, 80% of my research is on Gaussian processes. So I really like them. Where's the PCA? Was that L18? 1 second. We seem to have a technical error. Aha. Sorry. I seem to have somehow messed things up. Did I actually update the title? Yes. Nothing like writing your lectures in the actual lecture. There we go. So let's try that now. I just included the wrong file, I believe. What happened to Control L being view full screen? Full screen mode, okay. So, I don't have the BibTeX. Let me just do the BibTeX because that shouldn't take any time. So, what we're going to do in this period is, oh no, there's no, okay, we can't do the BibTeX. So I've messed that up. So Hotelling in 1936, which is what that question mark should say, introduced something he called principal component analysis. And that's what we're going to talk about next. I think that the history of this is important. People reference Pearson, but I don't really, Pearson is a statistician in 1909. I don't think, the contribution I'm interested in Hotelling, first of all, he introduced the name, and he introduced this way of understanding what's going on, which to me is what a latent variable model is. And I want to use PCA as a latent variable model. PCA has several interpretations, but Hotelling, as far as I'm concerned, is the man, because it's 1936. At the time, people are interested in factor analysis, and they're interested in trying to understand intelligence. What is factor analysis? Well, or say, for example, a good example is intelligence. So factor analysis was an idea that came out of the social sciences, which says, for example, that your intelligence or your personality is made up from some underlying factors. And then I mean, people do these tests, these personality tests. They're based on this idea that you're either introvert or extrovert, you're intuitive or judgmental or something like that. These sort of things, INTP, ENTJ. It's all this type of idea. So if we did a personality test where we ask you lots of questions, do you like working in a field or do you like working at a desk? Do you like, would you prefer to be a window cleaner or a bus conductor, you know, and then they associate how much this is indicated. They look at all this data and they say, oh, well, people are grouped into two different types. There's some groups of people that like working at a desk, some people like working outdoors. And the way they analyze this data is trying to say, well, what are the underlying factors that are determining how people are? And they talk about this as factor analysis. So your personality is defined into these different factors. So Hotelling was at the time when this was popular in social sciences, and he was actually a mathematician statistician. And he said two things. He said, first of all, let's not call these factors, because that means something in maths. Now, it turns out, actually, it does mean the same thing in this case. Let's call them components. And then he was a bit more formal a bit about how he described the problem. So this is a quote from his paper. It's a bit more technical. So consider p variables, which is our data. It's p variables in our data. The statistical variables T1, T2 to TP might be scores made by school children in tests of speed and skill involving various arithmetical problems or problems in reading. They might be physical properties of telephone poles. You know, they're features. They're our data. It is natural to ask if there is some more fundamental set of independent variables exist, perhaps fewer in number than the t's, which determine the values that t will take. So if those are defined by x1 to x2, then what he says is you've got each t, the ith t, is a function of x1, x2, x3, blah, blah, blah. Quantities such as the x's have been called mental factors in recent psychological literature. So really psychology was driving this forward. But this guy is a mathematician. So, however, in the prospect of psychology application of these ideas, conflicting use of the word factor in mathematics, it would be better to simply call the x's components of the complex depicted by the test. So he sort of says, let's look for the principal components that are forcing this function. So he's got some sort of input, and he's seeing some observed output, and he wants to know what the principal components are driving that. So to make things simple, he actually then says, we'll make t a linear function of x. Now, what I want you to notice here is up until now, we've been saying one output. So t was w transpose x, where w was a vector. But here, to make t's now going to be a vector as well. Each data point has a large number of features. So w is now a matrix. And w, if there's p elements in t and q elements in x, so there are q factors and p observed tests, then w is a matrix which is p times q. We know that because x is a little vector of these factors. It's inputs. So it's like in the regression, just as before. X is inputs. But now they're unknown. We don't know what x is. So x is sort of what's going on in your head or something. And then we observe the results from your test. And t could be, for example, your exam scores across your entire degree. Yeah? So you might be someone who's good at maths, not so good at writing essays. If those are the two components to determine your exam scores, we could then fit all your exam scores using this sort of analysis. So t would be every score you had, and then your x, your personal x, would be something we could derive from the data. Then you can also add a mean, so that there's a mean to everything, and also noise. So noise is coming from a Gaussian distribution, let's say. So this is a dimensionality reduction. And what I want you to think of as this being is a mapping from x, the latent space, to t, the data space. So here it's a two-dimensional to a three-dimensional. And because there's a linear mapping, the matrix W actually defines a plane in the three-dimensional space. Yeah? So the data's here, and your latent factors are here. So good at maths, good at essays is over here, and then that projects in your marks to something over here. Where that projects to depends on what those different exams are. If those exams are testing your ability in maths and essays, then if that's all they ever test, you would expect all the marks to lie on this two-dimensional space because there's nothing else to test. Now, then there'd be a little bit of noise, which depend on whether you were ill that day or whatever else is affecting your exam scores. So everything wouldn't sit exactly on this plane, but they would sit near this plane. So that's a picture to have in your head, that's what's going on in a principal component analysis model, but it's typically going on in much higher dimensions. So typically you can't draw what this looks like because you don't just have 3 exams, you've got 20 exams or something. Okay? Now, the cool thing about this is almost exactly the same likelihood as linear regression. So, if you look at the ith data point, the ith feature, sorry, the ith data points, so this would be the ith student and their jth exam mark. If we're just looking at the jth exam mark only, so we consider one exam, it's just linear regression. Okay, and we know that we can actually, this mu can also be absorbed into the x, but we're keeping it separate here because we don't want to use this basis function interpretation for reasons we'll find in a moment. So we're keeping the mu separate. So how do we deal with these unknown factors? Well, in linear regression, to do Bayesian linear regression, we used a prior over the matrix W. We said that we're going to sample from W to find out what the weights of our regression function are. In principal component analysis, we put the prior on the other place. The unknown thing is x. So what we say is that the setup for creating a student, if we're modeling a student, is first of all, we sample their ability in maths from a Gaussian. And we keep that Gaussian to have a variance of 1. Why do we keep it to have a variance of 1? Well, because actually this is all a relative thing. It doesn't matter how we scale. We're going to scale those things by W. So by keeping the variance to always be 1, we remove some scale invariance. We're just saying, okay, your ability in maths is sampled from a Gaussian between 0 and 1, and then basically you would know if someone's better than you at maths, they'd have a higher score on that. It's really more the relative ordering of those things which would be important, not the absolute value of the ability in maths, as it were. Then we do the same for your ability at essay writing. I've got those two things. And then whatever else we're interested in. So for every individual, we just take a sample from a Gaussian to determine these things. That means we can actually write the joint prior distribution. We could actually write it as independent in both dimensions. But here I'm choosing to write it as independent across data points. And the prior distribution over x can be written as a multivariate Gaussian with a spherical unit covariance for all these things, yeah? So it's convenient to write it as a product over n for the maths that follows. Now, what we're going to do, hopefully now, is recreate the maths that allows us to find this result. Now, I want you to look at this result a little bit before, because hopefully I want you to see that although this is a new bit of maths, it's just the same as the old bit of maths. Okay? So before, we were doing a Gaussian system where we put a prior distribution over W, and we obtained the marginal likelihood, and the marginal likelihood gave us a form that had a covariance which was x transpose plus sigma squared I. Well, looky here. We're putting a prior distribution over x, and now our result has the form of a Gaussian. Okay, we've included the mean now. Because we've included the mean doesn't disappear. That makes it slightly more complicated. But a Gaussian with a covariance which is W transpose plus sigma squared I. It just happens because W and X always appear together as this inner product. If you put a Gaussian prior over that, or a Gaussian prior over that, okay, this one's indexed in a different way. That's indexed over features, and this is indexed over data points. But the maths ends up working out the same. Can you believe that's going to be the case? So what I'm trying to explain to you is we're going to do a completely different derivation that's going to be exactly the same, apart from x's and w's will be substituted and all these sort of things will move around. Okay? So we're going to compute the marginal likelihood for principal component analysis, which will allow us to uncover what W is. So bear in mind, when we do maximum likelihood in this system, we're looking to maximize the likelihood with respect to W now, not with respect to the prior parameters. So what we're optimizing with respect to and what we're integrating out has changed. But the derivation is, as long as you can generalize, which you can because you're humans, not computers, the derivation is broadly speaking the same. Okay? So let's have a go at doing that. Well, let's just see what I've got on the rest of the slides. Okay. Now, the problem once you get here is actually you need to do maximum likelihood on the resulting marginal likelihood to find out what W is. That's not something we're going to cover. We're going to look at it in the course. It's not something I'm going to expect you to reproduce. It's a different looking derivation. It involves knowing about singular value decompositions and some manipulation. So it's not something we're going to cover today. We'll see in general if there's time. Okay. Right. Does everyone follow that so far, just before I move on? So we're looking at a different type of model, but the derivation's similar. Any questions? Okay, so let's see if I can remember the likelihood. Okay, so we've got probability of t, but t is now, yes. So let's be careful before we start. I hate using t for data, but it's something that Chris does and Trevor did, so we're doing it. So t now, it's got n rows, p columns. We were using p for x before, but we're using it for t now. And in this is like the different scores, so t11 to t1p, that's like your score in the machine learning course, and that's like your score in, I don't know, computational systems biology or whatever Magnus's course is. And there's all these scores in between, and these are the different students, for example, and these things going along here are, so these are the different exams, and these are the different students. So there's n students and p scores. So your data is now in a matrix, whereas before we just had one of these, one-dimensional, yeah? So slight change. So we've got a probability distribution over all data, given all the latent variables, the matrix W, and some noise. And let's just check. How do we define? We said that W, so T is so this is helpful doing this, sort of writing these little bits down. T is n by p. X is now going to be the factors. It's in the same form of T, but it's going to be n, so it's the same number of rows, but there's Q latent hidden factors. I should save this, just in case I forget. Okay, so W on the other hand, I think I can work this out, but let me just double check which way around we define W so that I don't make you write down something that's wrong. So W must be, because T is p-dimensional, W must be P times Q. Yeah. Sounds right. Oh, this stuff about this big funny R just means it's in the real numbers. So that's what the R means. You can ignore that if you like. Okay? Now the probability of an individual Tij, so this is the ith student in the jth exam, given W, so this will be the J, comma, colon. So what do I mean by this colon notation? Well, it's stolen from MATLAB and Python. So we had that matrix Y before, right? If I want the first row and the entire set of columns from Y, it's that. If I want the first column and the entire row, it's that. But we never, so here the result is actually a row vector. In Python it isn't, it's just a vector. But we never use row vectors. Never ever think you're writing down a row vector. Everything, once it's a vector, is a column vector, okay? So this is a column vector, even though it's taken from the jth row of W. Now the cool thing about this is actually there's something called matrix factorization. And it's very clear, and this is used for recommender systems, Netflix, and it's very clear that that's actually what's going on here as well. It's not, so that's the, damn, I don't need the transpose, comma, I need that in a bit. Okay, so those are the sort of inputs, and that shouldn't be an I, and what we're saying is that this thing here is going to be Gaussian Tij minus Wj comma colon x transpose xi comma colon squared over sigma squared. So this is just like the standard regression likelihood we've been writing down, but in the regression likelihood there was only one W, yeah? There was just one vector W, we didn't have a matrix of W's, and there was just one vector of outputs. So we're just adding this index J. But what we need to do here now is ask the question, what does the ith data point likelihood look like? And it's important you get this the right way round. So now we've got the whole matrix W. So we're asking for the vector of features for a given student. What's the distribution of a given student's exam marks, given W, and that student's latent skills? Now we're going to use independence, but the independence is going to be across the data features. So this is one data vector, and what we're going to have is the product of each of these. The same independence assumption we've been using normally across data points, but now it's going to be across data features, and that leads us to this form. And we get this same effect of so there's P features in this model. The product becomes a sum in the exponential. Just keep doing the same things again and again in these derivations. Okay, and I've moved the sigma squared out. Okay, lo and behold, we need to combine that with the prior over W. Okay, so why did there's also, bear in mind that there's also a independence assumption over the data points. But it turns out this whole thing factorizes over the independence assumption on the data points. So I think I'll come back to that, but just I want you to see that we've managed to, with the independence over data features, we've managed to get the whole of W in here, which is the important bit. Because we've now got a prior distribution over W, which you also using independence assumptions have said is going to be Gaussian with a unit variance. So there's no sigma squared or anything. We just get a P Q over 2. So if it's independent across every element of W, you have to go down all the rows and across all the columns. So you get a PQ appearing there because there's PQ elements in W. Minus a half of sum of what we're going to do is make sure we've got this same sum over J okay, so I should probably have done that little bit in stages. So that comes from the sum of j equals 1 to p on the sum of I equals 1 to q of wij squared. Because the Gaussian is independent over each wij. And then when we multiply them all together, we just get one sum over q, one sum over p. Now we can write that in either way. We can write that as the sum over q. So this form here is rewritable as wj transpose wj. So it's just a matrix representation of that form, yeah? Because this is an inner product, it's just wji times wji plus all the summed across all the i's. So that's the case. So that gives us a prior I've gone completely the wrong way. Sorry. Bugger. I'm so busy doing regression. Who didn't point out that we're not doing regression anymore? So I'm doing multivariate regression here. Bugger. So this should be over x. I was just looking at the next step, thinking the next step doesn't work. So everything I've said is true, apart from the fact that we're going over x. Why didn't someone mention that? Because I'm speaking so confidently that you think I know what I'm doing. There you go. Never think I know what I'm doing. Bugger. Teach me not to make more notes. Where are we? So the prior is, of course, in this case, it's supposed to be over x, not over it's colon comma I, colon comma j, x colon comma j, not over w. And actually the point is that then factorizes into 1 over, so in fact I think that's a bit of a wild goose chase I've sent you along there, sorry. Right, okay, bugger that. Fortunately this can all be cut from the actual final lecture we put online. Okay, so the prior we're going to use is, we've got to do prior over x, each data point xi, is Gaussian, but it's again, I mean, everything I said was true if we were putting a prior over w, but it isn't a prior over w. If we look at the ith data point xi, then there's q elements of that. And then up here, we get the sum across J. So J here, there's Q columns in X squared like that. Sorry. It's easier than I was making it out to be. Which then can be rewritten as that. And this is independent across n. So there's another product over n, but we haven't included it. The reason we haven't included it is because there's also a product over n on this guy. So what I want to show you is that since we've got, sorry, if people got that down, I'll try and keep that on the screen. So what you can do is you can do this marginal likelihood given W comma sigma squared factorizes over all the data. So the independence assumption doesn't need to be put in across the data points, doesn't need to be put in until after we've done the integral. Yeah? So in the regression we had to deal with the this independence before we did the integral because you couldn't factorize it like this. The result didn't factorize. In fact, the result is you get correlations across n. But here, the result factorizes across those n data points. And what we want to use is this guy. And I should have written that down in the first place, then I wouldn't have gone on to make that silly error. This guy. Where this guy is P of X, I comma colon. And we'll do that because we're running out of time now. Because I took you on a wild goose chase. We'll do that next time. So these are the two sort of parts to get that overall likelihood. We need this guy here, and we need this guy. Okay? So we'll finish that on Tuesday. That'll give us the marginal likelihood for principal component analysis. I think you'll then have covered, I need to double check, but I think then you'll have covered everything I want you to look at in the terms of the derivations. There'll be a bit more discussion about what PCA can be used for. And depending on how we get on with that material on Friday, I'm going to use Friday to make sure we've covered everything I wanted to cover. And then now you've got these concepts as what I'm going to do is I'm going to show you a lot of stuff that you won't understand directly how you get it, but you should understand your intuition. So I'll show you where all this leads. I mean, I don't want you to sort of think, oh, I have to understand, you know, on Friday, we'll definitely need to use Friday, some of Friday, for finishing off the material on PCA, I suspect. But then the rest of Friday, what I'll use it for is saying, okay, now you've got these type of models, what can you do? Because in some sense, I've given you the fundamentals for all the research I do. So what I'd like to be able to do is show you some of that research on Friday. But hopefully you wouldn't be able to understand it all on Friday, because that would be 10 years of my career that you understood within the space of an hour. But hopefully you'll enjoy it and understand why this material is important, because you can do some really special things if you understand it well. Okay? Good.